Hey, how y'all doing? Okay, let's think. It's about time to start up. I think everything's set and it's recording, and like normal, I want to start with any questions that you have related to content or administrative matters. And always I like to go with administrative matters first because sometimes those things feel a little more pressing. Any of you got questions on administrative things? Okay. How about questions related to content from yesterday? And in particular, the lab from yesterday would seem to be a very reasonable set of things to ask about. Okay. Then what I'm going to do is the normal thing of attempting to share a screen. And because I made some changes on my computer, I might very well accidentally share the wrong screen. I'm going to try and share the right one. I have to remember I changed what I call desktop 1 versus desktop 2 for some reason. And hopefully this will share what I want. Okay, yeah, that's about right. Good. And now that I'm sharing that, I just want to draw your attention to, well, here's where we're at in the course material. And within our week 3B, which is combining these categorical and quantitative variables, I wanted to sort of, because in chapter 7, we're going to get into chapter 7 a little bit today. And I want you to tackle the lab associated with the interactions between categorical and quantitative variables today. But because we're not going too much deeper, I will talk on a little bit on interactions in a general sense between two categorical variables, but the more complex case of interactions between quantitative variables, we will be putting on hold until this coming Monday. And because that, I'm not going to have any new homework problems out of chapter 7 assigned today to be due on Monday. I want to assign them on Monday because they sort of match a little bit better what we're going to do in class on Monday. Okay. So with that in mind, I want to sort of dive right in with new content, unless, again, one of you wants to stop me to ask about the lab from last time. If I can do this right, I can actually, open up this thing about interactions. Maybe I should take that guy and move it off to the side. Smallify. Okay, so interactions. You've already seen interactions once in the lab earlier this week, where you tackled the pig weight gain data. And you might have spotted that the change between the no vitamin B and vitamin B case, the weight gain between no vitamin B and having vitamin B, seemed to be different in the yes antibiotic group and in the no antibiotic group. That's an interaction. Let's say it again, but a little bit differently. The effect of antibiotics, yes or no, is different if you have vitamin B than if you don't. Okay. In general, whenever you have any situation where the effect of one variable depends on a different variable's value, you would say you have an interaction between those two X variables. Here's a quick example that some of you may be familiar with, but if you're not, guess what? It's probably worth being familiar with. The impact of heart disease medication on the benefit of a patient, if you will, the reduction in plaque, depends on which medication it is. Well, and that's no surprise there. different medications are differently beneficial. And it may depend on the sex of the person involved, but there may be even an interaction between them. If you were going to go with the word model, the change of plaque, it depends on the medication you use and the sex of the patient. But because of this thing, this interaction with the little star here, an asterisk, if you will, that says the effect of which medication may be different between the two sexes. Yeah, interaction. The effect of one thing may depend on another. Now, I'll try this for all of you, but this will not go over well unless some of you are willing to participate. Now, with the hands up, actual physical hand, I can't really tell. But if you are either able to show yourself on camera or to hover above that reactions button, because in the reactions button, you can sort of raise your hand or lower your hand. You can also sort of use a green check or a red X, any way of indicating things that would help me work through this. How many of you are from, let's say, Los Angeles, or better yet, further south, like Orange County, San Diego? Any of you? And when I say south, I mean south compared to me. So we got at least Alexandra. Good. How many of you are from, let's just say, San Francisco or northward? Okay, Brenna, perfect. So we got one of each. At least, okay, maybe more than one of each. And there's a version of this that I could, describe for people who are from the Valley, but it's probably a lot better to just go with the SoCal or NoCal. If I said, I'm going to drive from here to Disneyland, you're thinking San Luis Obispo to Disneyland. Does the route that I take impact how long it takes to get there? The obvious answer is, well, duh. But of the routes that I could take, are there some routes that I would be certain to take if I knew there was no traffic? I mean, I don't know where you're from, Alexandra, but I'm assuming that you've gone past Disneyland on I-5 at some point in time in your life. I'm thinking I would take I-5 southbound. Yeah, literally, I guess 101 to Interstate 5, and that's right near downtown Los Angeles where there are interchanges, and then you just head south and you hit Disneyland eventually. And I know someone who claims they can do it in 3 hours, slow to Disneyland. I'm thinking they're probably driving in the middle of the night, though, because I know there's traffic at many times during the day. So if I asked you, is it best to take that route? You'd probably say, well, it depends on the time of day. Because if it's during, let's just say nominally 4 to 6 p.m. when you're heading into the Los Angeles area, you might not want to choose taking a 101 to 5 southbound. Okay, so I'm going to sort of spit off what route I would probably be taking. But honestly, I would probably use Waze, that app that somehow steers me different directions than I had originally planned on going, because the traffic is better some routes than others. I'd probably end up 101 to 405 southbound, to 10 east, to 110 south, to 105 east, to like 710 south to 91 east to 5 south. So that's like a zigzag thing, right? I don't know that that's the fastest route, but I guarantee you the effect of which route that you're taking depends on the time of day. Let's talk about Northern California. Suppose I want to go to Santa Rosa for fun because I've got family that live there. Or let's suppose I want to go to Santa Rosa because it's an obligation because I have family that live there. Which route should I take? Some of you are thinking, well, you just take 101 all the way up. Others of you are saying, well, you know what? Probably you don't take 101 all the way up. You might take a different route because most any point in time in the day, 101, as you head into San Francisco, becomes a real gnarly pain in the ass as you get through the city. And so some of you would say you take 101 up to, I guess, 380 near the airport, then cut over to 280 northbound. That drops you out on 19th Street through Golden Gate Park, then across Golden Gate Bridge, and you're back on 101 by there. Would that be a reasonable route to take? Brenna says yes. I take it you've done this before. Okay, but if it's traffic in San Jose, Brenna, would you probably take 85 just past Morgan Hill and take 85 to 280, skipping 101 through the whole of San Jose, through the whole of Silicon Valley? Would that be maybe a better route?
Yeah, regardless of 101, I'd just take 280 anyway.
I do too, because I prefer that route. But if it was 2 in the morning, 101 to 380 to 280 northbound, then through the city is going to be a little bit quicker. You could save about 10 minutes if it's 2 a.m. by taking 101 a greater stretch. If it's not, I mean, sort of 10 a.m., 1 a.m., if it's not 1 a.m. or 2 a.m., probably going around the bulk of Silicon Valley, the southern end of it, if you will, and then sort of and the very western end of the populated area along the peninsula, that's going to save some time. So the effect of which route you take depends on the time of day. The time of day variable maybe impacts the time it takes you to get to your destination, because sometimes a day it's like extra traffic because it's rush hour. Other times a day it's not rush hour. But which route you take, its effect depends on the time of day. That would be an interaction. So let me show you an example of an interaction. And this is because we're talking about drive time, commute time, traffic, that sort of thing. At one point in time, one summer, I did a summer course where we had 5 weeks, 5 days per week. And so I had 25 minus one holiday, July 4th, days worth of data. Okay, so I, in 24 days, drove from Los Osos to San Luis. Literally, would I get in the car and turn on the ignition, set the timer, and when I get out of the car, I wouldn't say door to door, but when I get out of my car at the parking lot in San Luis, and this was always, I aimed for the same parking lot just because that would make it fair. Okay. Which parking lot it is just doesn't matter. It's the same parking lot. So I'm doing a fair commute time calculation. Okay. So commute time in minutes, I rounded to the nearest minute. How long did it take me? And I either chose to leave at 6:30, 7:30, or 8:30 a.m. And the route that I took from Los Osos into SLO, I guess to Cal Poly, was Los Osos Valley Road, and then Foothill into town, then somehow to that parking lot. Or I would take primarily Highway 1. So my two routes are take Los Osos Valley Road and Highway 1. Two routes, which one's best? Time I leave, 6:30, 7:30, 8:30. Which one's best? Well, you're thinking probably earlier, less traffic, even during the summer. Commute time should be lower. If I were to explore the data graphically, we could get a better sense for what's going on. And I always recommend Graph Builder for some reason. Maybe it's because I find it helpful. If my goal is to understand what the data are trying to yell out at me, Graph Builder is a good thing. I'm going to use commute time here, and I'm going to use commute time as a quantitative response. The time I leave is 6:30, 7:30, 8:30. I mean, whether I use this as quantitative or the categorical variation that I'm showing you here, it probably doesn't really matter because the dots would be in the same spot. And I'm going to sort of have the routes correspond to the two different overlays, the two different, if you will, color. And then, well, if I add a dashy line, it's going to sort of draw things a little bit differently. That's going to show me the average for each of these different times of day. But if I just show you the dots, you're spotting a couple things. One is Los Osos Valley Road is saving time versus Highway 1. So far, so good. Number two, 6:30 leaving then is a little bit quicker than if I leave at 7:30. Well, at least for the one route, or 8:30. So the effect of route is well, it takes more time to do the blue route, Highway 1, than the red route, Los Osos Valley Road. Time of day, well, it's less commute time at 6:30 or 7:30 than it is at 8:30, certainly. If I were to do the analysis, and this is going to look like that pig data model that you fit, the commute time could depend on the route I take. Well, yeah, of course. It could depend on the time that I leave. Yeah. And I'm going to say maybe there's an interaction between route and the time I leave. I'm going to cross those two. My word equation is sort of what GMP spits out at you, or like the way you input things into GMP. Commute time equals route plus time that I leave plus route times time that I leave. If I run that model, a lot of output that I don't need to see all of. So again, I'm going to focus you in on what matters most to me for right now. One of those things is your R squared number. That says we're explaining an awful lot. I guess we look at parameter estimates sometimes. I usually like those expanded estimates just because it's easy for me to forget that maybe one of the variables is not being displayed. The analysis of variance for the model says across my whole model shows 2 routes, so 1 degree of freedom for route, 3 times that I could leave, so 2 degrees of freedom for that. And this interaction seems to have 2 degrees of freedom attached to it. I've got 5 overall degrees of freedom for my model. At least one of the terms in my model is noticeably benefiting me. Which one is it? Well, our effects test may allow us to spot that. You may also be wondering, well, hold on, is this balanced or not? You might have spotted that it is. But if I wanted to convince you of that, I could then, under estimates, display the sequential tests. And notice that my sequential tests, sums of squares, F ratios, everything is the same as my effects test. So I don't really need to do the sequential approach. I could use my default adjusted sums of squares. And if I wanted to, I could give a sequential sums of squares result. Like I could say, you know what, the route that I take matters. I could also say the time that I leave matters. I would probably want to use a sequential sums of squares interpretation of this interaction. I'd say controlling for the route that you take and the time that you leave. Certainly the effect of the route on the commute time depends on the time of day. Okay. So these complex terms, maybe they should follow the simpler terms, and perhaps we should use a sequential approach and say controlling for those other lower order or easier terms. So looking at my model, I've got this mess, if you will. The average commute time, 24 minutes. If I take Highway 1, well, shoot, I spent an extra 2 minutes, 2.33 minutes, 2 minutes and 20 seconds. But if I take Los Osos Valley Road, it's saving me 2 minutes and 33 seconds compared to the average. If I leave at 6:30, it saves me 1 3/4 minutes, or like a minute and 45 seconds compared to the average. If I take leave at 8:30, it costs me an extra 2 minutes and 2.25 minutes, or 2 minutes 15 seconds. But these interaction effects here, there's something that we would also need to incorporate. It's almost like, and I like our prediction expression style of things. Show prediction expression, boom. You'd say, you know what? It's going to take me about 24 minutes. But if I take this route, Highway 1, it'll cost me an extra 2 minutes and 20 seconds. And if I leave at 8:30, it's going to cost me an additional 2 minutes and 25 seconds. And if I take Highway 1 and leave at 8:30, well, we're going to subtract off 0.083 of a minute, if you will, 5 seconds. 0.083 of a minute, is that 5 seconds? No, that's 10 seconds. Okay. Some of you are doing the math in your head and you're saying, dude, you're close. But in any case, you subtract off some seconds because of the interaction. And whether you're on Highway 1, leaving at 6:30, 7:30, or 8:30, there is an interaction effect you need to add in. Or if you're taking Los Angeles Valley Road, whichever time you leave, there is an interaction effect that you would need to factor in as well. The nicest thing that we have for describing what's going on is either an interaction plot, like you explored in that lab, and shoot, that's too small to read. Maybe let's make it big. 6:30, 7:30, 8:30, Los Angeles Valley Road. There's a bit of a savings. If I take Los Angeles Valley Road, if I leave at 7:30, the savings by taking Los Angeles Valley Road is even bigger. And if I leave at 8:30, well, it's smaller than it was at 7:30, but it's a hair bigger than if I left at 6:30. So my favorite route saves me time, but I'm really sure to go out of my way to take Los Angeles Valley Road if I'm leaving at 7:30. If for fun I want to swing through Morro Bay, I'm much more willing to consider that at 6:30 than at 7:30 in the morning, because that's a huge extra cost, if you will. Okay, so we could get into the weeds with that. Let me show you one other trick that we're going to emphasize on Monday as well, under estimates. I'm sorry, under factor profiling. Let's use this thing called a profiler. Again, down at the very bottom, and I like to grab it and bring it over here to make it big enough that I could read it real easily. In this factor profiler, and let's just make it smaller. And okay, so small enough, and maybe there we go. Okay, so we can see shown here, if you are leaving at 6:30 and taking Highway 1, your estimated time is 24 minutes. Your confidence interval for the average time of the commute is 23.21 minutes. It could be as much as 24.72 minutes. Let's suppose you were to take Los Angeles Valley Road instead. I'm just sort of going to drag it over here. My line that was at Highway 1, I'm going to drag it over to Los Angeles Valley Road. It says you're only taking 20 minutes and a half. And my confidence interval for the average is here displayed for me. You could say if instead of 6:30 that I'm leaving, what if I'm going to leave at 7:30 or 8? We can spot the benefit of Highway 1, I'm sorry, Los Angeles Valley Road versus Highway 1 is smaller by a shallow slope, steeper, a bigger benefit, if you will, and then shallower at 8:30. And the fact that at 8:30 we're always higher does suggest it's going to take longer. So you can drag these hypothetical what ifs around to really get a sense for which situation is going to be the best. I think I would say the interaction plot, we could say we think there is an interaction if we have a lack of parallelness here or a lack of parallelness here. Downstairs, if I go from 6:30 to 7:30 to 8:30, if the slope changes, we have a lack of parallel. Or if I go from Highway 1 to Los Angeles Valley Road and Foothill, if the nature of the curve across 6:30, 7:30, 8:30, if that changes in shape, and it seems to change its shape from concave to convex and back and forth, you'd say, again, an interaction. Lastly, because we did want to know, is the interaction statistically significant in my FX test? You would say yes. We'll talk more about that one on Monday. That's a situation where it's entirely categorical explanatory variables, categorical route, categorical time of day in which I leave. Any questions about that example? Okay, because the lab today corresponds to an interaction between a categorical variable and a quantitative variable. We'll dive in on that example next. And quantitative interactions will be on Monday. So let's visit our friend income and life expectancy one more time. Again, we've got our OPEC and our industrialized countries. And There's life expectancy, and it may depend on income, and it may depend on the type of country. Let's fit a model and see what our data want to tell us. Actually, let's use Graph Builder and see what the data want to shout at us, if anything. Looking at graphs often allows you to say, what are the data really, what are they really saying? Income, life expectancy, you'd say, well, across the types. Maybe I'm going to make this straight lines. Two groups, certainly. There is a positive slope in each group, and the slopes are a little different. What would it mean if the slopes were not different? Well, the effective income would be the same regardless of the type of country. If the slopes are different, it's corresponding to the effective income is different between the country types. That would say interaction. So I want to know, is there an interaction, if you will? Are these slopes noticeably differing here? Do these slopes have a noticeable difference? We can try that with our model, fit model. Boom. Life expectancy could depend on, let's go with country type first and income second. It shouldn't really model. It shouldn't really matter. But I'm going to have income and type. I'm going to cross those to allow for the slopes to differ, the slope of income related to life expectancy to be different between the two types. Run that analysis, and I'll show you over here after I sort of eliminate the things I don't want. We do see, again, these two different trend lines. And it's sort of funny. Graph Builder says industrialized gets blue. Industrialized gets red over here in my regression, my model output. Don't worry about that. I'm going to ignore this guy. Look, different slopes. Is it statistically significant, those differences? I don't know. I would say if we add in a new variable, the interaction, we will increase our squared. Is it worth it? Well, across the three parameters of my model. So why are there three? There's the one slope. Okay. Then there's which group are you in? A second parameter, like higher or lower trend line. The third parameter that dictates how different are the slopes between the two lines. So that's three separate degrees of freedom. Is at least one of them mattering? Yes, that's the case. Under parameter estimates, you can do t-tests, if you will, but we've been trained to say we prefer to use our effects test. So let's use effects test downstairs. And let's get rid of the analysis variance overall and bring the effects test upwards. Aha! The effects test says between the two country types, there's a noticeable difference. If you control for income, and if you allow for an income interaction with type. That's a little goofy. That's a little goofy. That's really rather goofy if you think about it. Let me try income. I would say here, income isn't clearly going to matter. If you have type of country in your model and also an interaction between income and type, again, I don't see that as being all that helpful. It seems like with the effects test, I'm saying controlling for something that includes type, we say type matters. Doesn't feel right. Controlling for something that includes income, income doesn't matter. Perhaps we can, with a sequential set of estimates, grab onto things a little more cleanly. Let's read the sequential test. Is there a noticeable difference between the types? Hell yeah. Controlling for a possible difference between the two types, is there even a slope? I don't see a slope. I don't see a slope as necessary. If you allowed for a difference between the two types of countries and a possible slope within the countries, Is the slope different between the two countries? I don't see the slope as differing between those two countries. Two country types, I should say. If I were to change the order here, I'm going to try fit model one more time. I'm going to recall. Okay, so I had type first, income second, then the interaction. I'm going to go ahead and have income first. Yes. Then I'm going to put in type. And then I'm going to have a type income interaction afterwards. So income first, then type, then income type interaction. Again, over here, the wrong window, and I shrinkify, and let's zoom into, well, same picture shown to me. Same, so everything's the same. Oh, our effects tests still the same. Notice that the only difference now is the top row is now the second, and what was the second is now the top row. Everything else is identical in the effects or adjusted sums of squares procedure. What about under estimates? My sequential. I'll claim that, again, that one really hard to read and stomach. This one cleaner. If you have an interaction using sequential sums of squares and putting the interaction last is a good thing. So I will say it this way. Is there a noticeable trend relating income to the response? Yes, there is. If I were to include a slope, would there be a noticeable difference between the country types? Yes, there is. Third, if I had a slope and even had a difference between the two country types, do I gain anything by having a difference between the slopes in my two groups? I don't see one. There's a lot to be learned by comparing these two here. Really, if we put in country type first, you say income just doesn't seem to matter, and neither does the interaction. If you had income in first, income does seem to matter, and it's because the income is higher in one type country than in the other. So income seems to matter, but really it's country type that plays the key role here. Is there a benefit of country type above and beyond income? Yes, it proves itself as benefiting us, but there is no benefit of having the interaction. Any questions on that so far? Okay. Let's get after the real reason for doing this analysis here. There we go. If I were to tackle darn it, that's the lab. Okay, so let's just go ahead and dive right in on the algebra and then get you set up for the lab. And I'm going to work off of these parameter estimates. And that's it. I want to sort of get after, and maybe over here, I can show you the optimal amount of information. And over here, shrinkification. Like yesterday, I've got these two different groups, and I'm going to go with red and blue for the two different country types. First off, I'm going to write down my overall model, and that model is expectancy, EXP, equals 58.4, plus then 0.00144 times income. Okay, plus, well, shoot, one of two things, either an 8.6 if industrialized, or minus 8.6 if OPEC, O for OPEC. Plus, I've got one additional term now that I'm going to add in, and that is Industrial times income minus 27. Oh, that minus 2765. That's a real pain in the ass, isn't it? Haha. I don't want to have to subtract 2765 from the income before doing algebra like I had done last time. Let's try fixing that under Analyze Fit Model. You can, under recall, that's the model we fit. Okay. Notice here up on the very left under model specification, you see that this center polynomials is selected. I'm going to encourage you, for the sake of convenience of doing algebra, deselecting this is not always a bad thing. It will cause the results using JMP to be identical to the results if you were using Minitab, the software package our authors use for the analyses in their version of the textbook. If I sort of deselect, it's hard to really tell that anything happened. Let me just see. Oh, look, the center polynomials is no longer checked. If I were to run things now, it still looks similar as we had before. Let me look at what I need, and my parameter estimates is what I'm aiming for. Notice I've got still that 58. I'm going to do it this way. Haha. I've got that 58.4 for intercept. Yay. I've got 0.004144 times income. Somehow the impact of industrialized seems to have changed. So I need to swap out my old number. It's actually legitimate, but I cancel that. Cancel. Darn it. Okay. Okay. And now I can use the eraser. Okay. And I'm going to put in numbers that correspond to my analysis over here. 10.5. 10.5 if industrialized, minus 10.5 if OPEC. But what about this last separate thing? And I'm going to circle it in green. The industrialized interaction with income. I'm going to write that out the following way. I'm going to sort of put it in black now, even though I circled it in green. I'm going to say plus something times income. Okay, so I'm going to have plus one of two options, minus 0.0007. I'm sorry, 0.00067 minus 0.00067 if it's income and industrialized. So if it's industrialized, but we add in a 0.00067 if it's an OPEC country. Okay. Do y'all see the minus 0.00067 if income is attached to industrial? We're changing the slope here by 0.00067 downwards, but for the other group, we increase the slope. Let's show you the expanded estimates. Notice with those expanded estimates, we still have our let's see if I can get it right. We have still our negative 0.00067, but we've got the 0.00067 if upwards if it's OPEC. So OPEC seems to be more positively sloped, industrialized more negatively sloped than the average slope across the two separate groups. And we can see again the plus 10.5, the minus 10.5. So here's my model. And let's go ahead and look at my plot again. And let's calculate red or blue. Let's go with blue. No, let's go with red first because it's upstairs. So for the industrialized countries, so I, for industrialized countries, I'm just going to write down what my model is. Expectancy is 58.4 plus 0.00144 times income. plus 10.5. And I can ignore the minus 10.5 because it's an industrialized country. I don't have to pay attention to the OPEC information whatsoever. But then I minus 0.00067 times income. Shoot, darn it. I had a bit of an error here. I apologize for that. There we go. Now let's put it back, times income. Okay, so this is the effect on the slope of income. I should have the times income there. So I put it back in correctly. So there is a slope. And then there is the impact on the slope of it being industrialized. There's the intercept and the effect on the intercept of it being in an industrialized country. So I'm going to collect the like terms 58.4 plus then 10.5 things without income in them. Plus 0.00144. And I'm going to go with minus 0.00067 times then income. And this is where I maybe need a little bit of algebra help or calculator help from one of you. I'm going to need to know that. And I don't do that so well in my head. I can only approximate that in my head. The upstairs one I can get because that's 68.9. 68.9, that is my intercept. Plus, I've got a slope which is sort of positive 0.00144, but I have to decrease that slope by 0.00067. So 0.00144 minus 0.00067 gives me about a 0.0007 what?
Seven.
Seriously, that is so convenient. Times income. So here we go. Here is our, for our industrialized country, that is the actual relationship. That is the slope of that and the intercept of that red trend line. Yay. Do y'all feel happy like I feel? I should have seen at least a smiley face icon or emoji from one of you for that. Okay, fine. Okay, I've got my subtraction, my addition. I added to the intercept and I subtracted from the slope. I adjusted the intercept. I adjusted the slope because it was the one group over the other. This initial information that we have, the intercept and slope, that is the intercept and slope averaged across both groups as if each group had the same number of data points. Or I could rephrase that. If you were trying to predict the life expectancy of a country, and if I didn't tell you whether it was OPEC or industrialized, and if you thought each OPEC and industrialized was equally likely to be the sort of country that I'm giving you, that average intercept and the average slope is what you'd want to work with. But because you know we're talking about an industrialized country, you know you have to work with the industrialized trend line. We got it. Okay. So what I want to do is to clear just the necessary things and redo with blue. And the reason I like to do this is there's always someone who says, you know what, I saw that, that was easy, but could you do another example? Because, you know, another example is helpful for me. Okay, I feel successful because I did the whole thing myself. So let's go blue, and that's the OPEC countries. So OPEC. I'm going to write down just stuff that's relevant to the OPEC countries. So the life expectancy is 58.4. Well, that is the intercept on average across both groups, plus 0.00144 times income. Okay. But I'm now going to add in a negative 10.5 because it's an OPEC country. Again, you have the adjustment to the intersect of the country type. And we also have an adjustment to the slope associated with the country type, plus 0.00067 times then income. And you can imagine I'm going to need some calculator help here after I do my algebra. I've got 58.4 minus 10.5 plus 0.00144 plus then 0.00067 times income. And I can do the first one possibly in my head. That's going to give me 47.9-ish. Some of you are thinking, okay, yeah, you got it. So thank goodness I could get that. But I can only approximate this value as 0.0021, but I'm sure one of you could do better than that. 0.002 what? 21?
0.00211.
211?
Yeah.
Okay, so I will change that. Nope, I will erase it to make it look legible. Boom. Okay, there we go. We have an intercept and we have a slope. Well, and that line corresponds to the OPEC country relationship. Yeah. Okay. We're getting close to time to stop, but I wanted to work my way through this example entirely because on the lab today, you're going to be working with that Duncan data on occupational prestige again. And notice how you previously tried with Graph Builder, perhaps, to fit lines for each of the three groups. And you notice they had slightly different slopes, perhaps. You fit the model last time, the three parallel line model. And with the interaction test, you can see if there is a needed interaction, i.e., does at least one of the slopes differ from the other slopes? But you can also work from the parameter estimates to get to the intercepts and slopes of any of the three groups yourself. So I'm going to sort of save this and clear and emphasize one thing one more time. If I start with a model, and let's sort of repopulate our model with the recall button. I really love that recall button. If by default, you just look up there, the center polynomials is selected. That means it will give you an analysis that is inconvenient compared to what you want. Your analysis will look like something minus the average. This is called centering. Income minus 2765 is the way it chooses as a software package to center income. And there are really some notable benefits of doing that, but not for the exercise in the lab today. So I recommend before you run your analysis, you make sure that the center polynomials is deselected, verify that it's not checked, and then run to get the analyses that you are most going to find convenient. The algebra that I had done earlier, if I had my parameter estimates like this, that's 1, 2, 3, 4, no problem. I can work with that. I've got 1, 2, 3, 4, again, no problem. And I can work with that. But I would have an extra minus 2765 floating around inconveniently. It's more challenging to collect like terms. Again, terms without income in them and terms with income in them are the way we're going to deal with it here, just like in your lab. Okay, it is about 5 o'clock. Any quick questions before we call it a day, or better yet, a week? Okay, so what I'm going to do is stop the recording and